My name is Pradeep Kumar. I am the Oregon Chair for the Communication Society. Welcome, all of you, to this lunchtime series for an exciting presentation. I'd like to also welcome the many Comstock chapters who are co-hosting this event. We have Central Texas, Buenaventura, Seattle, Vancouver, British Columbia, Foothills, Orange County, San Francisco, Albuquerque, Sacramento Valley section, and the Oregon section, as well as Chicago and Pittsburgh section. I'm going to hand over to my vice chair, who will be the moderator, Dr. Ralph Vanathambi, is from Intel Corporation, and is also an IEEE fellow. So without further ado, I will hand over to Ralph.
All right. Thank you, Pradeep. I'm very happy to introduce our speaker today, Dr. Filip De Turck. He's a professor at the Department of Information Technology at Ghent University and IMAC in Belgium. His expertise are in the area of communication software, network resource management, adaptive multimedia service delivery, and next generation video delivery platforms. Filip was the chair of the IEEE Technical Committee on Network Operations and Management. And Filip served in the Technical Program Committee for many international conferences on network and service management. Filip also served as the editor-in-chief for the IEEE transactions on the network and service management. He has organized and also served as steering committee member for numerous, symposium and workshops and network operations and management, as well as network softwarization. And he has published, co-authored over 750 papers. And he also received the award from the Communication Society called Dan Stokesbury Award in 2021 for all his distinguished work in network resource management and network operations and management as well. And Filip is an IEEE fellow. Without any further ado, let's welcome our speaker.
Okay, many thanks, dear Rad, dear Pradeep, for the kind introduction. Appreciate it. Thank you for the invitation. So, a very good morning to all attendees. There is a 9-hour time difference, so for me it's past dinner time, and for you it's probably lunchtime at this moment. So let's start the presentation, and as a courtesy, I will start with a small welcome and a little word about my affiliation. So Ghent University is located in Belgium, so in Western Europe. Here you see the country map of Belgium, with Brussels in the middle is the capital city, and Ghent is in the northwest, near the coast. So it's a 45 minutes drive from Ghent to the coast. So it's a coast between England and mainland Europe. So Ghent University is founded more than 200 years ago. There are several rankings, and in one of these rankings, called the Shanghai ranking, Ghent University is ranked 84th place. So we are proud of this ranking. It's a comprehensive university, so not only technical university, not only engineering and business economics, but we also have faculty of medicine, law, and so on. So a large number of students, and in total 6,000 engineering students. As the chairman mentioned, I'm also affiliated with IMAC, which is a research institute in Flanders for nanoelectronics and digital technologies, which was founded 40 years ago. And there are more than 3,500 researchers in this area. So it's a virtual institute spanning multiple universities. They also have their headquarters in the city of Leuven in Belgium, and they work together with several universities who provide the necessary expertise in these domains. And my research group is called the ID Lab research group. So ID stands for Internet Technology and Data Science. Also has a double meaning, because we try to have many creative new ideas in our research group, and we have about 300 internet experts, data scientists, and we work together on many projects, and also with a lot of industry partners. So personally, I believe that working together with industry is very valuable. So I'm from academia, but I don't like purely academic work. I'm more intrigued by also working together with industry and trying to solve really relevant problems, short-term, but also long-term problems. It's important to find a balance there. But here you see just an overview of companies that we have a lot of collaboration with, but this is not an exhaustive list, and in total more than 500 collaborations have been going on between our research group and industry partners. So this is a short summary of what the chairman also provided. I'm happy to mention that I'm also an IEEE member for more than 25 years. So this allows also you to guess my age, because if you make a guess for the graduation date and then you add 25, then you will arrive at my estimated age. And as mentioned, I contributed a lot to IEEE technical committees, also organization committees. And for instance, I served as the chair for the technical committee on network operations and management within the ComSoc. And so this technical committee is one of the, in total, 28 technical committees. So here you have the entire overview of the ComSoc technical committees, and I highlighted here network operations and management. And of course, we had a lot of collaborations with other technical committees, because I believe it's good to have some overlap between the technical committees, but definitely there's also a strong need for collaboration between technical committees in organizing events, organizing special issues, organizing presentations, and so on. So I'm definitely in favor of this. And when my students are interested in a particular topic, then I always tell my students, please have a look at the technical committees of ComSoc or other societies. And then please also contact the people who organize these technical committees. And this is a very good entry point into a community. You can make contributions there, get to know people, start networking, collaborating with people. There are many people from industry in these technical committees, also from academia. So this is what I always recommend to people who ask me, how can I get involved into a community? Then I tell them, please have a look and contact the technical committee organizers. Okay, so my main area of expertise is network resource management for different types of application, and video streaming, holographic type communications is definitely a very important application. So in terms of network resource management, the main goal is to make efficient use of available resources. So this can be bandwidth of a link or CPU power of a machine, or memory of a virtual machine, and so on. So these are the resources that you have available for providing services to the end users. And we try to manage these resources in the most efficient way. And we also want to provide service guarantees so that the quality of the service is guaranteed. And this is especially important for video streaming and for holographic type communications, because you want low delays, you don't want large startup delays, you don't want frozen screens. It should be a smooth playout of videos and immersive video applications. So I designed a lot of efficient network resource management algorithms, methodologies, where we also use machine learning optimization techniques. And also, since several years, I also made a lot of contributions to softwarized networks, where we softwarize the networks. So I will give an example on the next pages. And the main idea of a softwarized network is that we bring virtualization concepts to the network. So very similar to cloud computing, where the advent of virtual machines and virtualization of computers really accelerated cloud computing. And the same here with virtualization, we also accelerate the flexibility and the other important metrics for network management. And especially in industry, there is a lot of interest in academia as well, but also in industry, these software networks are very important. And I will give an example next. And I also want to mention that I also wrote several papers on efficient placement of virtualized network functions. So virtualized network functions, abbreviated as VNFs. And let me now explain to you briefly. Probably some of you are already familiar, but let me briefly explain just to make sure that we are all on the same page here. So what is network function virtualization, NFV? The way I typically explain this to my students is by looking at a residential use case where we have a home environment. And in the home environment, we have an internet router. We have several screens, can be TV screens, but also computer screens. And we also have a set-top box, STB, for digital television. And if we look, for instance, at a router, is also called the home gateway, then this home gateway has several functions. So it contains a DHCP server for providing an internet address, also network address translation, router firewalling functionality, and also quality of experience monitoring, so that, for instance, if you stream videos or digital TV through the gateway, that you can monitor which quality of experience is this stream receiving. And if we look, for instance, at a set-top box for digital TV, then there is a decoder inside for decoding the video streams. There is also storage there, so hard disks and flash memory for storing multimedia content. There's also middleware for allowing you to interact through the remote control, to interact with the set-top box. And there is also a streaming client for streaming the decoded video to the screen. And so all of these functions, so in total, there are 8 functions here. These are called network functions. And if we virtualize these network functions, this means that they no longer run on these dedicated devices, but they run on a remote data center, for instance, operated by a service provider. And in this data center, these functions then run as software components. So no longer as hardware components, no longer dedicated hardware for these functions, but they just run as software components in a data center. And what are the main advantages? There are advantages for a network operator and also advantages for a service provider. So very important for the network operator is that we can maximize the resource utilization and optimize energy usage, because in the data center, we run these components for many simultaneous users instead of only one user or one household for a dedicated device. So the amount of users is much higher, and then we can also distribute them over the available servers, and in this way optimize energy usage. And also in terms of deployment, configuration, and updates, so maintenance of these software components, if we have to install an update, then we can easily do this overnight. And then all users, they have access to their updated network function. And this is much easier than when everything is installed in the homes. Much more difficult to make an update, a software update to these devices. And also there is a support for network as a service business model, So you can allocate priorities to the users, for instance, and depending on the amount they pay, they get better guarantees and so on. So it allows for better business models than in the original scenario. And also briefly for service providers, there are also two main advantages. So the first one is you can dynamically scale the network. So you can bring in more computing and storage resources if needed based on the service requirements. So there is a elasticity that you can make use of. And also in terms of time to market for services, this can be much faster when you make use of these virtualized environments. Okay, so this is an important topic, network function virtualization in softwarized networks. And I will definitely come back to this when I introduce holographic type communications to you. And before I do so, there is one more element that I would like to introduce. This is adaptive service delivery or adaptive video streaming. And this is a very important technology. It's also used by YouTube, Microsoft, Apple. They all make use of HTTP adaptive streaming for delivering their video services over the network. And the main idea is that the video stream is segmented in time in small chunks. So each chunk is, for instance, 4 to 10 seconds, for instance. And for each chunk, there is a low quality version, so indicated with number 1 here. There's also a medium quality version, indicated with number 2 here, and also a high quality version with number 3. So the higher the quality, the more bit rate that we need in order to transport it over the network. And if we have a lot of bandwidth available, then of course we will always select the highest quality. We will always select the video chunks number 3 to transport over the network. But for instance, if the available bandwidth is fluctuating, and this regularly happens, of course. So if we start with a relatively low bandwidth, then we can request at the client side. So at client side, we monitor which kind of bandwidth do we have available at our client display. And if the bandwidth we have available is low, then we will request the video chunk with the lowest quality, number 1, and then the next one as well. And then we observe that we have more bandwidth available, then we will request high quality, number 3, and then lower one, number 2, and then finally, again, number 1. So it's important that we have an algorithm at the client side, and the algorithm determines which quality we will request at a certain moment of time, depending on the estimation of the bandwidth that we have available. Okay. So let me now introduce volumetric media to you and a small evolution over time. So many of you still remember 2D video. For instance, here the user is playing a game on a 2D screen. And then the 360-degree video, where we have a much larger view and we are more immersed into the content. So immerse or immersiveness means to deep absorption into something such as an activity or a real or artificial environment. So for instance, this person is playing a racing game and he is really immersed into the game and has really a similar view as the person would have if he would be in the race car himself. And then the next evolution, which is very important, is volumetric media. This is a technique that captures 3-dimensional space. So we can display an object, and the user is wearing virtual reality glasses, goggles, and we can display an object, and the user can interact with the object as if the object is really there. And we can design applications where the user is really immersed into the application. So if we look a little bit in more detail into these volumetric applications, so what do these volumetric media provide? In traditional 3D images, there were only two static views which were synchronized. So there was a view for the left eye and a view for the right eye that need to be synchronized. And if we look at the hologram, then we add parallax, and parallax is the apparent displacement of an object because of a change in the observer's point of view. So if you change your observer's point of view a little bit by moving in a horizontal, vertical, or in a tilt position, then you have the feeling that the view of the object changes. And for instance, here you see the 6 different updates that you can make. So in 6 different directions, you can make an update in the observer point of view, and you see a different perspective of the object that is shown. So we also refer to this as the 6 degrees of freedom. In comparison to Zoom and Teams meetings like we are using today, which have 2 dimensions. So if we use holograms in the future, then we will need 6 degrees of freedom. And what are the typical use cases for holographic type communication? There are 3 important ones, but there are many more that we can think of. But the first one is holographic collaboration and conferencing. So this is called telepresence. So a person who is not physically there can be represented as a hologram. You can interact with the person as if the person would be physically there. So this is called holographic collaboration and conferencing. Then also in the healthcare domain, there are important use cases for telesurgeries, where surgeons on different locations work together to do a medical intervention, and also for remote patient monitoring, also for therapeutic applications. For instance, people with fear, anxiety disorders, for instance, fear of heights or fear of spiders and so on. And then by designing holographic type applications, therapists can try to help people to overcome their fears, their anxieties. And then last but not least, a very important use case is in the industry 4.0 or even 5.0 for remote industrial monitoring and management, so that you can remotely inspect objects that are produced, for instance, in a factory. And instead of going to the produced objects yourself and inspect them there, through holograms, you can inspect them remotely and control the operation of the factory remotely. And these holograms are not science fiction anymore. For instance, there is a German circus who is using elephants displayed as holograms. And it's really impressive. So all the attendees are very impressed by the holographic elephants. It's also much better for animal welfare. And also there is the iconic scene of Star Wars with Princess Leia, who is displayed as a hologram. So both the applications are local applications, so they are generated locally. They are not transported over a network. And if we look at the bandwidth requirements, so on the next page, I will show typical bandwidth requirements. And these are in the order of gigabits per second. And sometimes they are too high for remote access, and then we need a lot of compression to compress the holographic images before transporting over the network. So which are the typical bandwidth requirements for holographic type communications? So for instance, if we start from high definition television, 180p, there typically for a high quality view, we need 1 to 5 megabit per second. Then for 360 video, also referred to as 4K video, there we need 15 to 25 megabits per second. And then if we go to 16K, so on bigger streams, higher resolution, then we need 100 to 500 megabits per second for transporting over the network. And if we then come to holograms, and there are two important technologies for holograms. There is the point cloud technology. So there we have a set of data points in space, and all the points together, they represent a 3D shape or an object. So each point has a set of Cartesian coordinates, x, y, z. And so if we know all these coordinates, then we are able to display the object, taking parallax into account, so that we can display it as a hologram. And there, typically for one object, for instance, then we need about 500 megabits to 2 gigabits per second for transporting this over the network. And as you can see from the overview here, in point clouds, we mainly focus on the objects themselves, not on the environments, because really, if we focus on point clouds, we focus on the objects themselves and the different points that make up the object. And a second technology is the light fields technology. And there we aim to reconstruct the planoptic function. So this is a 5-dimensional function representing the intensity of light observed from every position and direction in the 3D space. And we start from a set of example images, and then based on this planoptic function, we were able to construct all these realistic images by indexing the appropriate light rays. So, but the amount of bandwidth that we need for a light field technology is much higher than for point clouds, 100 gigabits per second to even 2 terabits per second. So as you can see from these numbers, it's more common these days to focus on point cloud technologies. And we expect that light field technology will also be important in the future, but at this moment, mainly in research, also in industry, there is a lot of attention for point cloud technologies. And in Europe, there are also many ongoing research projects funded by the European Union. And one of these projects, for instance, is the SPIRIT project. It started in 2022, and it will end in next year, end of next year, 2025. And it's a consortium of 8 different partners. And it's led by IMEC, by my research group. So IMEC is the research lead, and we have partners from industry, also main telecommunication providers in Europe, like Deutsche Telekom. Also, Fraunhofer is there, so the video optimization research group of Fraunhofer. We have also Ericsson as the equipment provider, and also several universities are involved. And the main idea of SPIRIT is to enable real-time immersive telepresence. So telepresence means that we will show a hologram of a person who is not physically there, but you can interact with a hologram as if the person would be physically in the room. And in this research project, we focus on three main types of innovations. So on network layer innovations, I will give some examples of these, also on transport layer innovations, and also on the application and content security innovations to allow these real-time immersive telepresence applications. And what is the main technical point of view of the Spirit project is we focus on different virtual network functions. So in the beginning of the presentation, I explained you about virtual network functions, VNFs, and for enabling holographic-type communications over the network, we designed several virtual network functions, as you can see here, for allowing that that the users on this site can interact with users on the other sides through holograms that are displayed locally. And we have a virtual network function for compression and encoding of the volumetric video streams. Then we also have a VNF for transport, buffering, merging, and synchronization of the streams. Also, VNF for view prediction, so where we want to predict where a user will most probably view. So you follow the movement of the eyes of a user in a virtual environment, and then based on the trends that you observe, you can make a prediction where the user will look next. And for this point, of course, where you assume that the user will be looking at, there you will provide a very high quality. And then there are other areas in the virtual environment that are less important, and there you provide a lower quality. In this way, you can optimize the quality of experience for the end user. And then finally, we also have rendering and quality of experience monitoring that we need for making adaptations. So these are the different VNFs, and we can deploy them on a network. So we make use of edge computing. So we try to deploy these components as close to the end users as possible to minimize the delays. Because for very high quality telepresence applications, the delays should be really small. I will provide some typical numbers in the evaluation section. So this is a view of the Spirit platform where we will demonstrate between different sites. So in Deutsche Telekom in Berlin will be users, and also in London, close to London, University of Surrey, and we will demonstrate the telepresence application based on the software components and the virtual network functions that we developed during the project. So the different use cases are listed here. So the first one is real-time human-to-human interactions. So these are also called holographic conversations. And the typical ones, typical use cases are listed here. And then in Industry 4.0 or 5.0 applications, it's also important that we can have human-machine interactions. And there can be two types. Can be human-initiated, for instance, for multi-site machine supervision, where the humans are in control, and they are supported by autonomous mobile robots for intralogistics inside the factory. But the interactions can also be machine-initiated. For instance, autonomous mobile robots who alert humans to solve contextual problems and to help them in understanding a situation. So these are the use cases that we will demonstrate. And the interesting part about the Spirit project is also that third parties, so also other interested industry partners or academic partners who are interested to make use of the Spirit platform, they can also submit an application. And there is funding, as you can see here on the slides, for 10 projects this year, and also 15 projects next year, where we target several application domains. So if there are companies, industry partners, or academic partners who are interested in evaluating their application or contributing to the Spirit use cases by making use of the Spirit platform and demonstrating it for their own applications. And we, for instance, we look at healthcare applications, retail, educational applications, training, also entertainment can also be part, like the German circus with the elephants, as I explained, also for manufacturing and even in the tourism business for remote visiting interesting places. So if you're interested, feel free to contact me for this. Okay, so let's now have a look at an important question. So I showed you the bandwidth numbers, and probably a main question that you have in mind is if you see these high numbers, then a very important question is the current transport and application infrastructure able to deal with volumetric media delivery? And in our lab, we did an experiment with different point cloud objects. So for instance, here you see 2 point cloud objects, and in total we considered 4. And for conveying this information over the network, so conveying the entire point cloud over the network, this requires a little bit less than 20 gigabits per second. So really significant amount of data that is needed. And we designed an adaptive streaming technique. So with the algorithm that I explained in the beginning. So at the client side, here we have a user wearing the virtual reality glasses, and who wants to view content that is stored on another place connected to the network. So this can be in another country, even across the ocean. We want to display this content, and we can add an extra dimension here. So for each object, we can also add a low quality, medium quality, and high quality version. So not only as a function of time, but also as a function of the objects. So in total, we had 4 objects, which you can clearly see here on the Z-axis. We also have 4 different objects here where we can select the video quality. And then if we want to display the 4 objects, then for each of them, we need to select the quality. So for each of the 4 objects, we select, depending on the available bandwidth, which quality that we can show for the 4 objects. And then in our lab, we evaluated the quality by means of subjective studies. So we involved a lot of users, and we displayed the holograms, and we also emulated network scenarios. So different configurations per video, where we changed the available bandwidth, the allocation of the bandwidth, and also the view prediction algorithms. And we asked many users to give their opinion on the quality. So they provided a quality score for the applications that we have in mind. And here you see the main observations, and you see the the subjective scores. So the MOS scores, which are the typical scores. And if you give a score, typically it's on axis of 5. So from 0 to 5, can also be represented on a scale from 0 to 100. And so a very good quality is higher than 4 on 5 or 80 on 100. And if you are below 3 on 5 or 2 on 5, like you see here, then the quality is mediocre, and the user don't really like the quality. So we really want a MOS score of 4, close to 5, if possible. We also see the cumulative distribution function here for different scenarios. So a scenario with low available bandwidth, medium available bandwidth, high bandwidth available, or even unlimited bandwidth available. So in a local streaming scenario where there is no bandwidth limitation. And what's important here is that the subjects in their subjective evaluations can distinguish between the different bit rates, but the difference in the quality of experience is not significant. And also people do not perceive delivered data as good quality. So the MOS score is too low, as I mentioned. So what does this mean to the network? It means that even if we have very high bandwidth available, then still we are not yet able to display and transport holograms in a decent way. And the main reason is that the techniques that we use, they don't cater to the latency requirements. So we need very low latencies. And this was not possible in the setup that we used. So if we make use of application layer approaches, then we also need at the transport layer and at the network layer, we also need techniques to make sure that latency is very low. And for this reason, we present a cross-layer based end-to-end architecture for volumetric media delivery that is really needed. So a cross-layer approach with optimizations on different parts of the of the layers to optimize the volumetric media delivery. So let me have a look at how we can achieve such a truly immersive volumetric video delivery and a cross-layer approach. And I see that.
Can I interrupt and ask
Sure,
a
sure.
question? Yeah. So,
Sure,
you're
you're right.
talking about, a few different things. One is like, streaming, and the other one is holographic and all. They have a different set of, requirements and challenges, right? One is like, holographic, I think, like, human holographic, very real time, and the requirements and the latency and the bandwidth and pretty high compared to the video streaming or streaming applications where you mentioned you can use those adaptive and
Yeah.
those kind of techniques. So maybe can you differentiate okay, what kind of techniques work for adaptive technique? Would it work for holographic? Oh, what kind of new things you needed for
Yeah.
holographic? Yeah, thank you.
Yeah, that's a very good question. Thank you very much for this. So as I indeed showed, it's not possible if you make use of the adaptive video streaming techniques. They are not sufficient. So there is a need for more techniques at several layers. And I will give a few examples next, but of course I keep an eye on the time, so I will not exceed the time. But it's also important to take into account that some streaming techniques, they are focused on optimizing quality, and other streaming techniques, they're focused on optimizing delays. And of course, both are important when we talk about volumetric media delivery, both. So both quality and latency are very important. And then it's interesting to design techniques that take the best of both worlds. And there are examples of these, and let me maybe go to these to just show you how interesting they are. So if we focus on a cross-layer approach, then here we have a holographic end user on one side and a holographic end user at the other side. So here are different cameras to capture the user, and then the content is encoded and decoded on the other side and displayed there as a hologram. And so in terms of optimizations, we have optimizations at the end user side to optimize delays and bandwidths. We also have optimizations at the transport layer, also over the top optimizations. And there are also novel network architectures that are needed for minimizing delays. For instance, distributed network architectures based on software-defined networks, and also virtualized network functions where we make use of SFCs. Service function chains where we deploy them in the most efficient way. And we need optimizations in all these layers in order to be able to transport volumetric media in the most efficient way with a high quality to the end users. So if we focus on only one layer, this will not be sufficient. So we really need a cross-layer approach where we focus on optimizations on multiple layers. And this also brings a nice challenge because we need collaboration between different experts, different types of industry partners in order to be able to reach the goal of truly immersive holographic type communications. So I'm aware that the time limit is approaching, Rad. So maybe a few more minutes before I close, and then
we
Sure,
don't want,
sure.
I think you should present, what you already have, as more questions comes, we'll think about it. Otherwise, please, continue and finish, continue your presentation. Yeah.
Yeah. Okay. Good. Okay. So let me make a selection because I will not be able to present it to the very end. But let me make a small summary of the main messages. Indeed, thank you for this. So in terms of end user optimizations, so let me explain now for the 3 different layers. Let me explain which optimizations that we have in mind. So for end user optimizations, there's a distinction between client-side optimizations and server-side optimizations. So at the client side, we have different feeds. So we have a visual feed, audio feed, and a tactile feed. For instance, we have haptic gloves that the user is wearing, as you can see here, and can receive signals. If, for instance, if you grab an object, then the haptic gloves give you a signal that confirms that you grabbed an object, for instance. And so it's important that we have the following optimizations. So viewport prediction optimization, so that we can predict where the user will most likely watch the content. So there we can provide a high quality video there. Also, synchronization of the feeds is very important. So this should be optimized. And also very importantly, and this is an important topic currently going on, is that we need a cyber sickness assessment, so that we need to make a prediction that the user might feel unwell based on the content that is displayed. For instance, if a user thinks that an object is there, but the object is a little bit at another distance that you didn't expect, then the user might feel a bit dizzy. So there is a lot of interest nowadays in cyber sickness prediction and prevention for holographic type communications. And once we know the viewport info and the quality that the user requests, we can also do server-side optimizations. And there are 2 important ones. It's tiling of objects, so where objects are cut into different tiles, and for each tile there can be a different quality. So the most important tile will have the highest quality, and the other tiles can have a lower quality. And we also can make use of multiple representations encoding to lower the bitrate requirements. And in terms of the over the top and transport optimizations, there it's important to take into account that we need to make a trade-off between quality and delay. So as high quality as possible, but the delay should be not too high. And for instance, if we look at the adaptive streaming techniques, so HTTP adaptive streaming, there the main focus is on quality optimization and not on delay optimization. So it's not really suited for real-time video delivery. Whereas there are also other techniques like real-time protocol, RTP, UDP streaming, where the focus is really on latency optimization. And for instance, there is the WebRTC framework together with the quick transport protocol provided by Google. Then we can synchronize multiple clients, and with a very low delay, we can stream content over the network. But there are also drawbacks, like there is very low resilience. When we lose packets, it's very hard to compensate for them. So the main idea is it possible to get the both or the best of both worlds? And if we succeed in this, then we really have a solid protocol for video streaming over networks with low latency. And there are several important transport layer optimizations. So there is a low latency transport where we have HTTP over QUIC, for example, or more intelligent buffering techniques, window-based buffering instead of the traditional buffering, where we can take the elements in the buffer that are really important at a certain moment, high priority, and that we are not stuck to take always the first elements in the buffer, but we can really go in an intelligent way to the information that we need in the buffer. And also smart retransmission techniques are also very important, like HTTP version 3, where we have a push mechanism, and we don't need to acknowledge each of the chunks of information, but we can push a lot of information and then receive an acknowledgement for all of them, and this really helps to reduce latencies. And then there is one more optimization that I would like to show you. It's a transport layer and control layer innovation, and it's called partially reliable quick, so abbreviated as quick PR, so partially reliable, or also referred to as QPR. So Q is the abbreviation for quick, the transport protocol by Google. And the main idea is that if you have a tiled video stream, for instance, this is a person on a skateboard or on a surfboard, and if you look at the content, most likely you will be looking at the person, how the person is behaving, how he is enjoying himself, and so these are the 2 or 4 tiles that will be most popular. So and there we want to provide the highest quality, and so we denote them as reliable delivery, and for the other tiles this can be less reliable. So if we lose some information there, it's not really a problem, because users will mostly be focused on this center of attention. And then we designed a new protocol for adaptive partially reliable delivery of immersive media over quick HTTP version 3, which has been published in an IEEE venue. Just briefly, I'm almost at the end, Rad, of my talk. So here you see an overview of different techniques that we can use. So where we compare HTTP2 with reliable quick and also with the partially reliable quick that we designed, and we see the throughput that we can achieve, also the cumulative distribution function. And as you can see, so the lines here in black and the dashed lines, they are able to achieve a much higher throughput than other ones. So this is the trace that's captured locally, but then when we distribute it over a network, then with the QPR technique, we are able to have a higher throughput. And also, if we look at the qualities of the different segments, So if we compare HTTP with reliable quick and partially reliable quick, we see that more of the objects are in higher quality distributed. So 5 is the highest quality. So there are more blue lines here with a higher quality. And then if we add more loss to the network, so that packets are lost in a random way, for instance, 2% loss, then we really see that the QPR technique is really outperforming the other ones, because for instance, the first one here, it's only the 4 objects are only displayed in the lowest quality, whereas in QPR, more of the objects are displayed in the highest quality, thanks to this technique that we designed. So this is an overview of different optimizations that are needed, and also there is a need for a service function chain optimizations, so different virtual network functions, and how to intelligently deploy them into a network to make sure that the latencies are low enough. So it's important that there is a good decision where you deploy virtual network function. Can be in a data center, can be in an edge cloud, can be in fog nodes. And it's important to minimize the end-to-end latency to really make sure that holographic type communications are possible. And this is what we currently are investigating in the European Spirit project. So I believe with this, Rats, apologies that it took a little bit more time than I expected, but I'm happy to pass the token to you, Rats, please.
Thank you. Thank you so much, Filip, for an interesting presentation. There are a couple of questions on the in the chat window. I can read one of them is, can on-device AI can be, incorporated for this type of question, solutions. I myself have a similar questions, how about, did you think about, semantic extractions and semantic communication, along with that question? Maybe you may answer.
Yeah. Okay. Very good question. Thank you. So definitely, AI is very important. Also semantics, especially there are a few examples. For instance, when we want to predict where a user will most likely watch the contents, their AI algorithms are very beneficial, and we already made use of deep learning algorithms, reinforcement learning algorithms. So we published a few papers on these to optimize the viewport prediction, because if you have better prediction algorithms where a user will most likely watch dynamically, then you have a lot more information where you should provide the highest quality, and this definitely is beneficial for optimizing quality of experience for the end users. So this is one example. And also in terms of deployments, where you deploy a virtual network function, you have several options. You can deploy it in a cloud. You can deploy it close to the end users in several edge clouds. There are many different locations where you can deploy your virtual network function. And depending on the choice you make, then this has a direct influence on the latency and how the user perceives the quality, and whether the user feels cyber sick or not. So if you can optimize this and learn over time through AI algorithms, make use of semantics as well, knowledge-based optimizations, then you can obtain much better quality levels and user perception of the applications.
Thank you, Filip. There's a couple of questions from Tom. Do you want to unmute and ask your questions?
Sure. Can you hear me?
We cannot hear you very well. A little bit louder, please.
Okay, maybe. Is this better?
Yes, thank you.
Okay,
Yeah, that's
headset.
better.
So I know that I'm going back to the elephant that you showed earlier. And so much of your presentation is about well, if we had this application and we had this bandwidth need, how would you address it? So that's all good, and I appreciate that, because you can't do this stuff without the network supporting it. But at the risk of sort of getting into the weeds on this one thing, this elephant, and I noticed that the article references also a Justin Timberlake concert where they had a hologram of Prince. I'm just wondering, does that actually exist as an application, or is that the common person sees something, they call it a hologram, they don't necessarily know what a hologram is, or what if it really is a hologram? I'm just wondering if this is a real thing that's out there, or it's an application that might happen someday if we were to develop the technology. Can you?
Yeah. Okay.
help?
Okay. That's a very good question. So at this moment, the German circus, it's not transported over the network, but it's artificial content created locally. So they have a few servers there, and there they generate the content, and through projections, they project the elephant shapes there locally. But there is no demonstration yet where they stream the elephant content over the network.
Yeah, I understand. And again,
Okay,
I'm sorry to get into the weeds, because your talk was really about the network, and so I mean, what you're describing to me sounds like what it is it's a video projection, a very complex one that must have been very impressive. But they're projecting ordinary images, I think, all recorded, all pre-recorded.
Pre-recorded, yes, definitely.
Yeah, all pre-recorded, just as any projector system does, and they need the servers perhaps because they have to show up and put this thing into place. It's a complex system. It works better to have a little localized network. But again, I'm not aware of any true holographic system. Maybe the point is moot though, because you say, well, if you have to deliver all this data, you'd probably do it in advance. You wouldn't necessarily do it in real time, but you could. So maybe your point is good. Holographic or not, it's a very, very big and video file.
Yes, yeah.
Or streaming application. So I guess I just a little, when I hear holographic, I'm optics guy, and I'm like, wait. So all right. Anyway, thanks a lot.
Thank you. Anybody else have any other questions for Filip before we wrap? All right. Thank you. There are other comments, you can read, Filip. People say like, your presentation was very clear, and, you talked slowly, and everything is clear, and very appreciative of that. In case if you read, I just wanted to,
I agree, by the way. That was really good.
Yeah. It's very good. Thank you. Thank you so much, Filip. It's very late in the night for you. Thank you again for taking the time and effort to give us this presentation.
And thank you for the invitation, and also for the feedback. Appreciate it.
Thank you. Thank you, Filip.
Thanks.